Let me give you a basic example just to show you how this whole procedure works. So let's say we want to compute this integral. It looks scary, doesn't it? But it has an inside. We can see the x cubed plus 5 as being the inside. And what is its derivative? Well, its derivative is 3x squared. Not quite just the x squared we have, but it smells close enough. So we're going to give it a try. So first of all, we're going to change the way this integral looks. And the first thing you want to do is, of course, get rid of that cube root. We know that when we're doing calculus, roots are not a good idea. So we're going to rewrite it in terms of fractional powers. So we're going to rewrite that same integral in this way. Secondly, we're going to identify the inside. Well, we just said the inside looks like x cubed plus 5. So we're going to set that to be equal to u. So u is going to be equal to x cubed plus 5. Next step, we're going to compute the differential. So du is going to be equal to the derivative of x cubed plus 5, which is 3x squared, times dx. Next, we're going to compute what dx is in terms of du. So that gives us du over 3x squared. And next is the big step. The big step is just substitute all these new things in terms of these new variables into the original formula. So we're going to start from the first one, from the original one, and we're going to say, okay, that's the integral of what? Well, first of all, we have our x squared. We're not quite sure what to make of it, so we're going to leave it there for the time being. Then the next piece is x cubed plus 5. Well, that's just u, isn't it? That's what we called u. So it's going to be u to the power 5/3 times dx. And what is dx? Well, we found out that dx was going to be du over 3x squared. Now we know what to make of that x squared at the beginning. We're simply going to cancel it with the x squared that we ended up with in the denominator. So we end up simply with 1/3. Of course, that 3 is a constant and can come out of the integral, times u to the 5/3 du. Alright, now we're dealing with an integral that we know how to integrate. So we're going to integrate it. So all we have to do is apply the power rule. And so it becomes 1/3 times 3/8 u to the 8/3 plus c. If you're not convinced, check the arithmetic. Alright, we can beautify that a little bit because we're still not done. So we may want to cancel those 3's and we end up with just 1/8 u to the 8 over 3. And now we have to do the last step, namely switch back to the original variable. So u will become once again x cubed plus 5, and here is our integral. If you don't believe me, well, check your answer by taking its derivative. Remember, whenever we compute an antiderivative, we can always double check it by computing its derivative and making sure that it works fine. There are a few issues to consider when it comes to this method of change of variable. Now, first of all, this method only works if the integrand comes from the chain rule. If it comes from a different kind of rule, it will not work. So it's just one possible method that will work if things work out fine, namely if the original integrand comes from a chain rule. Otherwise, we're going to have to use other methods. Of course, this is the only method we've seen so far, so it's the only one that up to now you will see in your exercises and quizzes and tests and so on. But pretty soon we're going to see other methods for integrating other kinds of functions for which this does not work. Also, remember there is that one step where I said if the new integral is in terms only of the new variable, then you integrate it. Well, if the old variable is not eliminated in the change, so remember in the example I gave you, if that x squared had not been cancelled, well, what do? You stop and you try other methods, or you try maybe a different substitution. You try something different, but absolutely don't try to keep going with an integral that has two different variables. You will simply just gonna end up with a mess, and with a definite mistake, and a major mistake at that. Also, the new variable that we use, that variable u, is going to be set equal to an inside piece. But sometimes we're going to have a choice. Maybe there are several pieces that can be thought of as inside pieces. What you may want to do is try all of the ones which are possible options and see if any of them works. At the beginning, even if none of them works, it's still a good practice because it will tell you a little bit more about when and how this method works. So keep in mind, usually you have more than one choice, and you may want to develop the ability of identifying which one is the most likely one to work. Finally, always check the final answer by differentiating it. Notice that this is a method. As such, it has several steps, and as such you may make a mistake at any one of those steps. So it's a good idea at the end to check that in fact the function, the antiderivative you found, is in fact the correct one. A few more points to consider relate to the terminology we're using here. This method is based on the general technique of substitution, and in fact it is also known by this name. Some people call it the method of substitution. In fact, I will call it the method of substitution every here and there. However, remember that substitution is a general mathematical technique. Okay, so it's something that we use in many situations. Okay, it's not just a method of integration. Okay, so keep in mind that change of variable is probably a better method, but it is longer. So sometimes if you want to use the method of substitution, that's fine too.